Okay, looks like some of you have already finished Lab 12. If not, I'll take that by lab today. I'm going to have Group A come in at 2 o'clock, Group B at 3. And you should perhaps plan on the more than the traditional 1 hour, because you're going to be performing the lab and doing the calculations today. So that may take you 2 hours. Maybe less if you're fast at doing calculations. The calculations really aren't that complex. I've already handed out the description of today's lab, and you can see that what we're going to be doing is looking at some of the fittings. We're just going to do a single flow rate, and so you'll be able to gather the measurements relatively quickly, but the purpose of the lab will be to compute the K value for each of these different fittings and then compare it to the typical K value that's provided on Table 1. So I would anticipate that maybe it'll take 40 minutes, 45 minutes to gather the data, and then the calculations, some of you will be done in 15 minutes, some of you will take your time and take a little bit longer than that. But anyways, lab is at 2 and 3. Any questions so far on the announcements? Yeah. It says on the handout there that all I need you to do is fill in the table and then provide the separate piece of paper to show the calculations you did to calculate K. So you can calculate K on a computer if you want to, and then you'd need to print out the spreadsheet, or you can do it on paper by hand almost as easily. So you'll do and have out of your hands the lab today. It won't be hanging over you. We'll just have it, and we'll be done. No more labs after today. Your final homework of the semester is due on Thursday. We'll go over a couple of those problems today. We'll look at the key ideas of them. But I've got office hours between now and then, and of course I'll be in the office tomorrow. Even though I don't have office hours, I'd be happy to help you if you want to check your work or have questions on that assignment. Feel free to stop by. Finally, our exam is on Thursday the 12th at 10:15. So that's a little more than a week from now. I guess it's 9 days. So, any questions? It's a comprehensive exam with additional emphasis on the material covered since the second exam. So there would be, on a per capita basis, so to speak, more coverage of Chapter 7 than the other chapters. So it's a 2-hour time frame we have for the exam. So in the previous exams, what have I given you? 4 questions? 3 and 4 questions? So since we've got added time and it's a longer exam, I would expect maybe to have 5 questions, 2 of which would be related to Chapter 7, which would be proportionally added emphasis, and then the other 3 material that's building on concepts up till now. You can bring your equation packet, and then like usual I'll also provide a few selected equations that maybe we've used through the semester but aren't in that FE equation packet. All right.
Can you bring that other equation sheet you gave us for the exam?
No. Nope.
Can we review that, like Wednesday?
No. No. Wednesday, you mean Wednesday the 11th? Yeah, I wish I could do that, but we're going to be in assessment meetings all day long. I'd much rather be teaching you a review lesson than in a faculty meeting, but literally it's scheduled from 9 a.m. until we all leave, so can't do that. All right, where we left off last time was talking about energy, power, and work. And specifically, I mentioned that when you have a system that's not 100% efficient, you have to make adjustments in either the power required to pump a fluid from place to place, or the power that can be generated when a fluid is moving from high elevation to low elevation. And that's the case here. Illustrated here is a turbine, and we are given in this example an upper reservoir elevation and that would be like the elevation above sea level, lower reservoir elevation. And ordinarily, we'd have to calculate the head loss through a channel, but in this case, just for simplicity's sake, it's given as a constant. It's saying that under these conditions, the amount of energy loss as water flows through this penstock channel is 5.4 feet. But as we talked about previously, that would depend on the velocity, the length of the channel, the roughness of it, the diameter, and so on. Under this situation, the flow velocity through the penstock is 7.4 feet per second. And what we want to find out is how much electricity can be generated if this turbine system is 70% efficient. And that's maybe in the ballpark of a typical efficiency that you could expect. You know, maybe a really nice new system would have a higher efficiency than that. But let's take a look at using both the power equation and correcting for efficiency, how much electricity could be generated in a hydropower situation like this. What we're going to be applying is the energy equation. And last time we talked about a couple of aspects of the energy equation that I'm going to not bother to write. Remember, we talked about the difference between velocity and average velocity. Average velocity means the average velocity across some cross-section of pipe. So there's going to be a whole lot of different velocities through the pipe because of turbulent flow, but we're saying the average across the cross-section. But it's common for people to write the energy equation without the bar above the V. Also, I'm not going to even bother keeping track of alpha. Remember, alpha, which is the kinetic energy correction factor of 1.05, we apply really in instances where we have a high degree of confidence in the precision of the data that we're using, and we're trying to be extra precise in the calculations that we're doing. But commonly, the energy equation, rather than the full-blown version that we've seen before, would maybe be written just like this. All right. So you can notice that alpha isn't applied to the velocity head term, and we didn't have the bar over the V. We're just going to assume that the velocity at certain points is the average velocity. So here, if we apply the energy equation between the two reservoirs, location 1 is always the upstream location. Location 2 is always the downstream location. Remember that this equation has a directionality assumed that you have to honor, otherwise you're going to get the wrong answer. And the directionality is that flow goes from 1 towards 2. And the reason why it's important that it's that way is that we're putting the head loss on the right side of the equation. We're saying that the energy at 1 is equal to the energy at 2 plus the head loss. In other words, the energy at 2 is lower than energy at 1 because of the head loss that's occurred, unless maybe there's also a pump or a turbine changing the energy situation. Okay, so here 1 is going to be the reservoir where the elevation is 4324.4, 4324.4 feet. The pressure head will be 0 because I'm picking as location 1 the surface of the water at that upper reservoir. And the pressure of the water at the surface is just atmospheric pressure, or 0 gauge. Also, the velocity head is 0. So I guess it's extra justified we didn't bother keeping track of alpha, because the water isn't moving in the reservoir. The water's moving through the pipe, of course, but V1 is not talking about the velocity through the pipe. V1 is talking about what is the velocity. You've got this big reservoir here. It's saying what's the velocity at location 1. And in the reservoir, the water's not moving. There's maybe a little bit of water moving towards the exit here. But since that reservoir is so big relative to the flow that's going through the penstock, the velocity at 1 is 0. So that's why I can neglect the velocity head term entirely. Now here we don't have a pump, but we do have a turbine. So I'm going to put 0 for the pump term. And location 2 is here at this reservoir surface. So it's the lower reservoir again. The pressure head is 0. we can just write in the elevation that's given, 4191.9 feet. Velocity head term is 0. Now, it is removing some head through the turbine. So H sub t is the unknown. What we're going to be finding is how much energy can the turbine extract from the situation if we have the head loss given as 5.4 feet. So there's potential energy as the elevation. Got the second elevation, the energy that's lost due to pipe friction through the penstock, and we can find from that H sub t is 127.1 feet of head. And remember, we sometimes refer to piezometric pressure in terms of head. Head is the amount of energy that exists in a hydraulic system, and if we had a pipe that we tapped with a piezometer, the water level would rise to a certain elevation equal to how much head there is in the system. The same thing is true of static conditions, that at the turbine there's a certain amount of head available for the turbine to extract. And this is how much we're going to have the turbine extracting. Now, the power equation is simply the flow rate times the unit weight of water times H sub t. Now, if this was a pump problem rather than a turbine problem, then we'd substitute in H sub p instead of H sub t. You know, if we were trying to pump water from the lower reservoir up towards the upper reservoir, then we'd switch the two. But in this case, it's a turbine, and so we have the information we need to calculate the flow rate, for example. Q equals AV, as we know, and the area can be calculated. It's pi d, and d is 3.5 feet squared divided by 4 times 7.4 feet per second. That area is 9.621 square feet, and the overall flow rate is 71.2 cubic feet per second. All right. So the flow rate of 71.2 cubic feet per second. The unit weight of water, we'll just use the 62.4 pounds of force per cubic foot for the unit weight of water. And then finally, the head that's available is 127.1 feet. So what are going to be the units of this power that we get out? We're going to have the cubic feet cancel out, so it's going to be foot pounds per second will be the units of power. The power that we have is 564,660 foot pounds per second. In terms of traditional units, there's a different unit of power that's far more common or that we recognize more readily, and that is the horsepower. Anybody know how many foot-pounds per second are in a horsepower? It's on the tip of your tongue, right? Close, 550. And of course, why wouldn't it be 550 foot-pounds of force per second? It just rolls off the tongue like 43,560 square feet in an acre, or 5,280 feet in a mile, or 12 inches in a foot. So 550 foot-pounds per second. So we'll divide this by 550 foot-pounds per second per horsepower, and we get that this is 1026.7 horsepower. So that's how much power can be generated if you don't account for efficiency. Okay, if the system was 100% efficient, then we could extract 1026.7 horsepower. Now forget what I've given you here and just reason through it logically. If it's 70% efficient, should we divide by 0.7 to find out how much power we can generate, or should we multiply by 0.7? What makes the most sense? That this is how much if 100% efficient. But the problem statement says it's only 70% efficient. It's not 100% efficient. So should we divide that by 0.7 to get our final answer, or multiply? Multiply, of course, because it's going to be, you get less power than if it was 100% efficient. So if we divided this by 0.7, then that would say that we actually got more power. But we know that it's going to be that you get less power since it's not 100% efficient. So if we have the 1026.7 horsepower divided by, oops, no, we multiply, 0.7, then we end up getting 718.7 horsepower is how much power can be extracted from the system. So we always want to get as much power as possible in a situation like this. So how can you generate more power? What are the ways to improve how much energy you can extract from this dam? Okay, if you had a bigger pipe, what would that allow you to do? And? There's one more step in between. So you have a bigger pipe, you've got more area, bigger flow rate. Because here's the power equation. The power equation says it's flow rate, unit weight of water, and the pump head that's available. So a bigger pipe would allow you to get more power. Of course, you have the risk of draining the reservoir. You know, it all depends on, do you have enough water to keep the system going? All right, what's another way that we could get more power? Do what? Change the fluid. Change it to mercury, something more dense. Yeah. So you could pour mercury into a reservoir and say, well, you're just trying to improve the, I wasn't polluting, I was, yeah, right. And then enjoy prison. Okay. Along with increasing Q directly, because if you make the area bigger, that's obviously going to change Q equals AV. Making the area bigger would also reduce the head loss, definitely. Because one of the, remember in the last lecture I said that next semester we're going to go deep with an equation called the Darcy-Weisbach equation. H sub F is F L V squared over D2G. And so if you make the pipe bigger, D is in the denominator here, that's going to reduce the head loss. And so probably if we had, instead of a 42-inch pipe, if we had, a 100-inch pipe, then the head loss would be lower than that. And so that energy that's thrown away to head loss, we could put right back into power. So if you lose 1 foot of head loss, that's like increasing the turbine head by a foot. It goes right back into head that can be harnessed. Or we could have changed the efficiency of the pump. It might be that there is a efficiency of the turbine, rather. Maybe there's a 75% efficient turbine. And so that would be an economic analysis to see if the additional cost of a more efficient system is justified by the additional value of the electricity that could be generated. You remember that project, don't you? Yeah, pump storage. I don't know. I still have nightmares from when I did the same project as an undergrad. Yeah, it was a good project. Which aspect? Oh, yeah, I basically defined things directly rather than leaving it too flexible, because Elman did, right? Yeah, if you guys took Engineering 221, you'd get a little taste of hydraulics. The safety guys and computer science don't like it so much, but I teach hydraulics even to the most unwilling of participants, every chance I get. Yes.
Like, thinking about like the head loss.
Uh-huh.
I don't really. Like, what exactly is that?
What is? Oh, okay.
Like, I don't remember that.
Well, that is the pipe friction. So that equation over here has units of feet. If we have length would be in F is unitless, so length is feet, velocity is feet. Velocity squared would be feet squared per second squared. D would be feet because that's a length property. And then G is feet per second squared. So feet per second squared. So the seconds cancel out. These 2 feet go away, and we just got feet left over. So that's a way of expressing that head loss is pipe friction. And it can be expressed in terms of a length parameter. Mm-hmm. Yeah. So let's see. I've got a good diagram of that. Is it in this last lecture? Let me go to one where I know it is. As water flows through a pipe, the pressure is decreasing because of the energy loss. And so this line represents the decrease of energy in the pipe. And since you can measure that line in terms of feet, how high above some datum it is, what we're saying is, between 2 points, how much energy was lost due to the pipe friction. That's just what goes into that, that head loss term of 5.4 in the example. Does that answer your question? Hopefully it'll get more clear as we talk more about energy grade lines today. Other questions? Yes? Absolutely. Yeah. You want to have a really, really high reservoir and a really, really low outlet. That gives you a lot more power capacity. And the problem here in the eastern United States where we live is that we don't really have big mountains. There are dams along the Mississippi River, for example. If you think about hydropower, but what's the problem? If this is the power equation, what's the problem in trying to harness electricity from the Mississippi River? The problem is that it's a very flat slope river, and so you can put in a little dam, but you're not going to have much of an elevation difference. And so what we have here in the eastern United States are called low head dams, because the way you're generating power is by having a big Q rather than a really big H. There isn't much elevation difference. Out in the western United States, in Colorado, Utah, Arizona, through the Rockies, they have these enormous elevation differences. And to a lesser extent, there are some hydropower stations in Virginia that have a reasonable high head to them. North Carolina. Yes, probably more than anything, a big elevation difference is the most important thing. Okay, let's just step to the side for a minute and talk about a couple of key ideas from the homework you've got due on Thursday. There are a couple of ways to analyze the question that they're asking. They show you a pipe. It's a vertical pipe with 2 pressure gauges. And they say that the pressure at the upper gauge is 10 kPa, and at the lower gauge is 98.1 kPa. And they're asking, is the flow up or is the flow down? And you don't, for your solution, you don't just write up. You have to actually show why it's up or why it's down. So the way that you can show that, first of all, you might just look at it in terms of what would the change in pressure be if it was hydrostatic? Because what we know is that in the hydrostatic equation, you can find delta P is delta H times gamma. So they give you a delta H, and you know that the liquid, I think in this case, is water. And so you can solve the problem sort of by a logical analysis and say, if the water wasn't moving, I'd have this change in pressure, but it's either greater than or less than that, and then that implies whether it's flowing up or down. That's one approach. The other approach here is to actually apply the full energy equation and say, well, remember my definition is flow is from 1 to 2. So pick one of the directions. Say, let's assume the flow is from B towards A. So this is location 1, and up there is location 2. Make that assumption and then start substituting things into the energy equation. Substitute in the pressures that are given. Substitute in the known elevations. You know, B is 0, A is 10. Now the velocity terms could be canceled out because the pipe diameter is constant, and so V1 and V2 are going to be the same. So you can just drop those terms out completely. Now what will be unknown is the head loss. There's no turbine, so that cancels out. There's no pump, but the head loss term will be unknown. You can solve for the head loss, and if the flow is from B towards A, like you assumed, then you'd get a positive value for head loss. But if you get a negative value for the head loss, that tells you that what you had assumed about which section is upstream and which section is downstream tells you your assumption is wrong, and that the flow is actually the other direction. Yeah, so you could solve it again, but then you just get that it's positive once you redo it with, you know, maybe A is 1 and B is 2. So it's a simple problem. Sometimes the simplest ones are the hardest to solve. One other tip that I'll give you for problem 721, they ask you to find out what is the flow rate through this pipe and also what's the pressure at location B, and then neglect head loss. In a way, I'm disappointed they told you to neglect head loss, because that's what Chapter 7 is all about, is, you know, head loss and the energy equation. Essentially, you could have solved this just using Bernoulli's equation, but, you know, that complaint aside, that they didn't include a head loss term for you, what you can do in this one is find the outlet velocity, because they're telling you there's some nozzle, and they give an elevation difference. And so this is essentially acting as an orifice. So you can find the flow rate out using the orifice equation. You know the cross-sectional area of the opening. And remember the orifice equation, velocity is the square root of 2gh. And so how do you find the flow rate from that? If you want Q, then Q is A times the square root of 2gh. So you can find the flow rate by the change in elevation and knowing the characteristics of that opening. And then to find the pressure at B, you just simply apply the energy equation between the nozzle and location B. Now, this will be one of those instances where you can't cancel out both of the velocity head terms. If B is location 1 and this opening is location 2, the velocities are going to be different because the pipe diameters are different. So don't cancel out V1 and V2 terms like we sometimes do when the pipe diameter is in the same diameter, like we did on the last problem that I just showed you. Okay. Any questions about this one and the key ideas?
Yeah, so you said find the pressure at B.
Uh-huh.
Start down here at the nozzle.
Yep.
You know the pressure 0.
You know the pressure, you know the velocity, you know the elevation.
Why can't we do it up there?
Well,
Give you a different
you
answer.
can. No, it won't give you a different answer. No, but you have to solve for the velocity here before you can go to B.
Right.
You couldn't find the pressure at B before you found the discharge in the pipe.
Yeah, I'm saying that if you started
Yeah, you could make this 1 and that 2. That'll be fine.
your Z terms will be different.
That's
Everything
okay.
else should be the same.
It'll work. It'll work. Do both. Prove it to yourself. Yeah. So you could either do, his question is, all right, we've got the tank, and here it's shooting out water. Okay, what I suggested was make this 1 and that 2. It will also work just fine if you have this be 1 and that be 2. Yeah, that's fine. Either one is okay. So what's different down here at this lower location? The water has velocity. and less elevation. Up at the top of the tank, it has more elevation but none of the velocity. So it balances out.
You said on velocity.
That's right. Because you have to know what's the velocity at B in order to put some velocity head term in there. Yeah.
And then when you're doing like the velocity of the orifice right here,
Uh-huh.
for your H term, we go all the way up to the...
All the way to the water surface. That's right. Yep. One of the fittings we're going to look at today back in the lab is we're going to be looking at an expansion. Remember, I briefly touched on in a previous lecture the difference between friction losses and local losses. A friction loss is distributed over the length of the pipe. So it occurs over some long distance, any place where the water's in touch with the pipe material. But a local loss is some reduction in pressure or a reduction in energy that occurs just at a single point. And what this diagram is illustrating is why you lose energy when water is flowing through a small pipe and expands to a big pipe. You'd think that maybe there wouldn't be any energy losses due to that. But what it's showing with the streamlines is that there's some turbulence there, a vortices around the edge, a zone of separation where that increased turbulence actually has a concentrated location of friction loss. There's going to be extra frictional losses. And so the way that you can calculate the energy loss there's two approaches. One is to find the difference in velocities between the two segments. And if you take that to the extreme and say that it's an expansion and it's a pipe entering a tank, so think about what happens when you've got a pipe that discharges into a tank like this. The water's moving along and it has a velocity head, but then as soon as the water discharges into the tank, all of the velocity head is lost. It just, poof, it vanishes. And so in this case, this would be 1, and in here is 2. And so V2 is going to be 0. And so when you have a pipe discharging into a tank, what I'm telling you is the energy loss is equal to the velocity head. When a pipe discharges into a tank, the head loss due to this fitting is V1 squared divided by 2G. All of the velocity head that was there just goes away. Energy isn't destroyed. It heats up the water very slightly, but it's not of any use to us any longer. Go ahead.
As far as these, going into a larger pipe, they were tapered.
Yeah, definitely. And that's a good point. And that applies not only to pipes, but to channels as well. So this is going to be worse than what if we had a gradual transition. So a gradual transition would have less turbulence, and so there would be less energy loss. And so the second way to account for the energy loss, instead of just saying it's the change in velocities, what we can say is that the head loss is K times V1 squared divided by 2G. And in a case like this, where here's V1 and here's V1, we just sort of instinctively know there's going to be less energy loss when it's tapered, so the K value would be smaller. Maybe here we'd apply a K value of 0.9, whereas here we'd say the K value for a nice transition is 0.5. In the lab today, you're going to be finding what is the K value for a sudden expansion. And also, we've got a sudden contraction that we'll look at as well. In the handout I gave you, it says that the K value for a sudden contraction, let's see, they say 0.4 for a contraction and 0.7 for a sudden enlargement. So I said 0.9. A more typical K value for a sudden enlargement would be 0.7. So in the lab today, we'll see if the pipes that we've got are typical or not. in the way that energy is lost. How are we going to measure energy loss?
Change the pressure.
Change in pressure. So it's going to be those pressure taps, the same way that you did with that experiment you designed. Remember the Hazen-Williams experiment where you were doing it between the 1 meter segments? We're going to go all around the pipe rack and measure the pressure difference at the fittings to find out how much energy is lost, and the energy loss manifests itself in a reduction of pressure. So this is a expansion. Now here's that diagram that I showed you of grade lines, and it's a way of visualizing how much energy there is in the system. What time do we finish? So confused. 12:15? Okay, all right. I sort of got out of the habit, you know, with Thanksgiving and everything. All right. Yeah, 11:45. I would have figured it out later, and oh man. Thursday. We're going to meet on Thursday, but I've already said that there won't be a quiz, right? Did I already tell you that? Yeah. But there might be a pop exam. Just no pop quizzes. No, there won't be a pop exam. All right. So what this is showing is a couple of things. First of all, this is a piezometer. The piezometer defines the hydraulic grade line. Why is the water level higher in this second tube? What's causing the water level? You know, the water level's higher even though the opening is further to the right. So presumably there's less energy here than there is there. So why does the water level raise higher? All right, it's a stagnation tube. So it's intercepting the flow, and the velocity head is pushing the water level up a little bit more. And so what you'll notice is that these two lines are parallel, but the energy grade line is above the hydraulic grade line by the velocity head. So this difference right here is v squared divided by 2g. If you know the velocity of flow through the pipe, square it, divided by 2g, you'll get some length parameter, and that's how much higher the EGL, energy grade line, should be above the HGL, hydraulic grade line. Okay, so stagnation tube versus just a standard pitot tube. I'm sorry, a standard piezometer. And the EGL and the HGL are the same at the water surface. Let me give you actually the formula for each, what they both include, and then how they're graphed will make sense to you. You've actually graphed them both before in the lab where we had the contracting section, and we had those tubes that were connected all over at different locations, and the water level rised up to a certain point, and it was illustrating what was the pressure, and the pressure started to recover, and then it was back to normal again. Okay, and we drew a graph. You remember that one. That was the HGL that you were graphing. And the HGL is the pressure head and the elevation head. The energy grade line, I'll write that formula above it since it's always above. EGL is the pressure head and the elevation head and also the velocity head. So the reason why the two lines are on top of each other here at the surface of the water is because it has no velocity. All of the energy is as elevation in a tank. It has no pressure. The water at the top, at the surface of the reservoir, there's no pressure. The water isn't moving, so there's no velocity head term. So the EGL and the HGL are coincident in the tank because it's both just the Z that you've got. Now there's this little location here. See that line that's where the HGL is dropping down? What that is expressing is the fact that when the water is to the left of the opening, it's got a little bit more pressure than when it's on the right of the opening. There's some energy lost as the water is entering the pipe. As the water gets sucked into the pipe, there's a little bit of a pressure loss, as the stationary water that was in the tank speeds up, there's a reduction in the pressure so that it can gain velocity. And so where that line is dropping down, that's just representing the reduction in pressure as the velocity increases. What they really maybe should have, yeah, I guess they're drawing it in the part of the pipe that's curved. Because in the pipe where the pipe is curved, you've got zero velocity and then it's increasing. Now, the slope of the line represents how quickly energy is being lost to pipe friction. And so if we had a pipe that was smaller diameter, if we were losing energy more rapidly, then that line would be steeper. If the line is very flat, that means that you're not losing very much energy through the pipe. When the water discharges out of a pipe, you'll notice that the HGL goes all the way to the water surface, but the EGL is above the water surface. The reason why this EGL is still above the water surface is because it still has velocity. This is a jet of water coming out, and so there's still some energy in the water that is equal to the velocity head. So the EGL remains above the jet as water exits. Let's look at a couple more. This is what happens when there's a pump. Water was going through the pipe, and so the slope here represents the fact that there's energy loss, and the EGL is above the HGL, but then suddenly both of them are shifted upwards in the magnitude of H sub P. H sub P is how much pump head is being added. It's the energy that goes into the system because of the pump, and it increases the pressure. That's how a pump adds energy. A pump does not add elevation, and a pump does not add velocity. Since these pipes are the same diameter, the velocity of water in the inlet pipe is equal to the velocity in the outlet pipe. These conditions are steady. The flow velocity is not changing with respect to time. And so how does the pump add energy? It adds it as pressure. The water pressure here is low, and the water pressure on the outlet side of the pump is very high. That's what the pump did, is it boosted up the pressure. And so pressure is in both of these terms. Pressure head term is in EGL and HGL. And so if the pressure goes up 100 kPa, then it's going to increase the EGL and the HGL by the same amount. And so you'll notice that these two had some certain distance apart. And by the way, what's this gap here represent? Velocity head. And so there's the same amount of velocity head on the outlet side of the pump as there was on the inlet side of the pump. And that's another way we know that the pump didn't speed up the water from inlet to outlet. The pump added pressure. And one of the representations of that is the fact that this gap between EGL and HGL is the same. And the pump just simply boosts up the energy on the outlet side. And then as water flows through the pipe, it's sloping downward, downward, downward as the pressure gradually decreases. Any questions about drawing these lines so far, or how to interpret them? Here's what happens when there's a turbine. Remember, we just worked in an example where there's a turbine. So the EGL and the HGL are at the surface of a reservoir. There's this little drop, this induction zone, where the HGL draws apart from the EGL as the water accelerates in the opening of the penstock. And then, why is it that this line isn't parallel to the pipe? The pipe is going down. Why is it that the EGL and the HGL, the slope is different than the slope of the pipe? It doesn't pertain to elevation. The slope of the EGL and HGL, it relates to the rate of energy loss due to pipe friction. That pipe is going to lose energy at the same rate whether it's horizontal or whether it's inclined. If you just say, here's location 1 and here's location 2, and it's going at V, versus here's 1 and here's 2, and it's going at the same V, the energy loss equation, FLV squared divided by D2G, That has nothing to do with whether it's flat or inclined. Energy, the rate of energy loss due to pipe friction is independent of the physical slope of the pipe. And so that's something that's important for me to point out to you, is that this slope is not talking about the pipe slope. It's talking about the rate of energy loss due to pipe friction. All of a sudden, there's a sudden drop in energy. The pressure in the outlet side of the turbine is much lower than the pressure on the inlet side of the turbine. And the way that works, remember, the inside here is like blades. It's got some spinning blades, and what's spinning them is the force of the water upstream of the blades. There's water on both sides of the blades, on the front and the back, but the pressure of the water on the front of the blade is much higher than the pressure on the back of the blade, and that's why it's able to spin when it's got the resistance of the generator on the other side of that turbine. You know, the generator has electrical resistance because of the load that's connected to it, and so it wouldn't spin if there wasn't a really high pressure on the face of that impeller. And so the pressure goes from really high to quite low. That's why there's a sudden drop in the EGL and the HGL. And then what's the interpretation of this, that these two lines are getting closer together? Remember, the distance apart of these lines represents what? Velocity head. So if they're getting closer together, what does that mean? So that tells us that the velocity is getting smaller. And that sort of matches up with what we can see from the drawing. It shows that the diameter of this outlet is increasing. Probably it's a baffle, so they don't have a big jet of water coming in and disturbing the gravel bed of this stream. They're gradually diffusing the flow by opening up the diameter. And so as the velocity decreases, then the head loss, the HGL and the EGL get closer together.
So the pump and the turbine are just to change the pressure?
That's right.
Nothing with velocity or anything?
That's right. Now, let me just explain one thing in a little bit more detail. All right. Here we've got a reservoir, and it's connected to another reservoir. Okay. You can tell that the water elevation of the reservoir here is higher than the reservoir elevation here. So here's a pipe. Will water flow from 1 to 2? Of course, because it's at a higher elevation. So water would flow from 1 to 2. It would flow faster if we put in a pump, right? The pump would make it flow a lot faster. So when I say that a pump doesn't increase the velocity, what I mean is that from between A and B, upstream of the pump versus downstream of the pump isn't changing the velocity in the pipe, but the pump can change the velocity compared to if there was no pump. Right. That is why the velocity doesn't change inside of the pipe. And so when I say that the pump doesn't change the velocity, what I mean is that the pump doesn't change the velocity of water in the pipe. But of course, the pump will change the velocity of water through the pipe compared to if there was no pump. But the way the pump works is not by increasing the velocity. The way the pump works is by boosting the pressure on the outlet side of the pump. So it's important to distinguish between those two. So Zach asked that, it was asking basically that the way the pump works is just by increasing pressure. And that's what this illustrates, is it increases the pressure, not the velocity. But of course, it increases the velocity compared to if there was no pump. So that's what's important to keep separate in your mind. Other questions about that? You know, I do encourage questions.
Would they, I don't know more about the power control the increasing resistance.
Yeah.
Can they, I don't know about, do they increase the coordinate?
I think that they do.
Steady.
I think that what they usually have at an actual power plant system is that the The turbine and the generator is most efficient at a certain number of RPMs, and so they'll have maybe 10 of them, and when the demand is low, they'll only direct flow through maybe a couple of them. Rather than have the same flow rate going through all 10, they would probably have a different flows running in parallel rather than reduce the flow through all of them. When there's, because the demand for electricity varies a lot during the day. Okay, this is showing what happens in a nozzle. This nozzle, as we know from the continuity relationship, if you have a big diameter tapering down to a small diameter, that means slow velocity and then high velocity. If the velocity is increasing, the velocity head is going up. And so the HGL and the EGL are getting further apart. So why is the HGL getting so low here? What part of the HGL? The HGL has pressure head and velocity head. So why is the HGL going down so much? Is this pipe friction that we're seeing? Marcus is almost going to say it. It's pressure. Why is the pressure going down so much? Well, kinda, but let's not look at the fact that it's jetting out. Before the jet, why is the pressure decreasing? It's the Bernoulli effect, because if the velocity goes up, the pressure has to go down. So what we're seeing is the manifestation of Bernoulli's effect. That's the same thing that we saw in the Venturi, when we did that Venturi experiment, that there was a big drop in the piezometer. So the piezometer was measuring the pressure head and the elevation. A piezometer is what draws the HGL. So as the velocity goes up, the pressure goes down. And then what Michelle said is that when it exits this nozzle, the pressure is 0. And that's true as well, is that when the water is in contact with the air, the jet doesn't have any pressure anymore. It's unpressurized. But the EGL is still present, and so it's above the water surface. Now what about this little section where we had a slope? What does the slope represent? Why is the EGL sloped? The rate of energy loss due to pipe friction. So why is it steeper here? It looks like it's steeper. Exactly right. The diameter is smaller, and the rate of friction loss is a function of velocity squared. That Darcy-Weisbach equation that I had on the board earlier, H sub F is FLV squared divided by D2G. This isn't anything you need to memorize for the final exam. I put it up on the board just to help explain why things are the way they are. We'll use this and learn it a lot more next semester, but what it shows is that energy loss is a function of velocity squared. And so when the water is going faster through that nozzle section, that increases the rate of energy loss due to friction. So they didn't show it that much steeper. They probably should have shown it a little bit steeper than that. But they do show that the rate of energy loss is different than when the pipe diameter was big. So here's a nice system that shows the EGL is relatively flat. The EGL and HGL is flat, and then it gets steeper. So it's steeper where you've got the smaller diameter pipe. The small diameter pipe has a faster rate of energy loss. At the outlet to this tank, earlier today, I told you that when water discharges into a tank, you lose all of the velocity head. And this is the drawing showing that. This is showing that the HGL intercepts the water surface, but then this energy loss that was, the velocity head that was there just instantly goes away. You go from having some velocity head to, once the water's in the tank, that velocity head is gone. We've got the nozzle that's accounting for that divergence. And this is another illustration that shows that regardless of where the pipe is, that the rate of energy loss due to pipe friction is constant. That's kind of interesting that if the pipe is above, if the physical location of the pipe is above the HGL, what that means is that you've got negative pressure inside of the pipe. And so you have a risk of cavitation because since the pipe is above the HGL here, then the gauge pressure is negative. Now, of course, the absolute pressure isn't negative, but if you measure the absolute pressure and it goes below the vapor pressure of the liquid, that's when the cavitation can occur. All right, we've already talked through these diagrams. So what I'd like to do is give you this handout so you can practice drawing EGL and HGLs. And then I'm going to show you what they ought to look like. So you've seen some of these in the previous slides just now. I'd recommend using a pencil because until you get the hang of it, it's pretty hard to draw these EGL and HGLs. There you go. Give it a shot. There's one on the front and one on the back. Yes, the big fat line on that front side means that the diameter is bigger on the second one. And the same thing's true on the back. The thicker line means a bigger diameter pipe. Yes. Well, is it a pump? It doesn't say. All we know is that the water is flowing from the lower reservoir to the upper reservoir. Yeah. I think Morgan knows whether it's a pump. He had a gleam in his eye. Let's take a look at the first one. See if you're headed in the right track. The EGL is going to be above the HGL, of course. So that's one characteristic I hope that you'll include. Another should be that they both start at the water surface on the left. And then it's kind of hard to draw this because what you've got to draw is two different slopes, but the HGL needs to finish at the water surface. And so in a way, it's kind of an iterative thing where you need to draw a shallower slope for this second segment because the pipe diameter is larger. Now, I showed that there's a sudden drop, and that's because of the expansion here. That pipe expansion, I'm saying that there's a sudden local loss accounting for the decrease in pressure there. And then the EGL and HGL are supposed to be parallel. My drawing skills aren't 100%. That may be that it kind of visually looks like it's maybe a little bit further apart here than it is there, but that's accidental, not by definition. And the HGL exits at the water surface. The EGL is a little bit above it. So that's what the drawing should look like on the first one. Yes? Well, there should be at least a little change in drop. It doesn't necessarily have to be as big as mine, but to be strictly correct, we do have a sudden expansion there. So, there is going to be some energy loss due to that expansion. So there should be some sort of a drop to show that. If it was super gradual, then, if it was gradual, then it would be less than the drop that's shown there.
It would just be one solid. I didn't notice it was like that.
Yeah. Right. When I put a problem like this on a quiz or an exam, what I'm looking for is certain indicators. Like maybe I'd assign 1 point if you showed that the slope was steeper for the small pipe than the other pipe. And maybe there'd be 1 point that's, that you have to have the EGL above the water surface, that it doesn't terminate into the water surface, but the EGL is above it. And maybe there's a 1 point for this induction zone here where the velocity is gradually increasing. And maybe 1 point for the sudden expansion and so on. So, it doesn't have to be that the sudden expansion, there's nothing magical about the actual slope that I've drawn here. It's relative. It's just that it should be steeper than the other one. Are there other questions on how to draw this first one? All right. Well, let me let you get back to it then on the second one. So what are the characteristics that ought to be there? Well, first thing that jumps out at you is that since it's a pump, there should be this sudden jump up. It's not a gradual thing. It's just instantly on the left side of the pump, there was low pressure, and on the right side of the pump, there's high pressure. So there's this vertical line where both the EGL and the HGL jump upwards.
Does it have to jump all the way down?
You first.
Does it have to jump all the way down?
No? No, it doesn't. So there's nothing magical about the fact that I've got the EGL and the HGL down to the pump level. As long as what I'm really looking for here is that this is steep, this one is steeper than the other one. But how high it jumps, it didn't necessarily have to jump as high as it did. It only has to jump high enough that you can have some slope and still make it into the tank. If it doesn't jump high enough, then water won't flow into the tank.
Hang on, this one's supposed to have a bigger gap than that one?
Yes, because since this is a small diameter pipe, there's going to be more velocity head. What was your question?
I might be just the way you drew it.
Yeah,
It should be the same.
parallel. It's supposed to be parallel. It is a little sloppy.
Well, I didn't know if maybe it was increasing.
Nope. Nope. It would be, they'd be diverging if the pipe was getting smaller, but it's not.
But that's supposed to be the same slope?
Yeah. Yeah, let's say it's that. Okay. No, you can keep them. It's for you. You put it on your fridge. I will see you at 2 o'clock, Group A for the lab, Group B at 3. Once we actually perform the experiment, then you're free to go into the lobby or get on one of the computers or wherever you like to do the calculations. You can stay back in the lab area for whatever you want to do. Then the homework's due on Thursday, and our final exam will be a week after that.
We pull that picture back up?
Yeah.